like live music, just the grunginess of it. That's the real music when they're performing it live. That was a group from actually they started in the 80s and they're still around, a group called Dinosaur Jr. In this video, I'm sure you're not here to talk about music, even though that might be more fun. In this video, we're going to talk about another important consideration when analyzing information, when doing an analysis of numerical data. Identifying the relationship between two variables. This relationship between two variables is also referred to, using some technical jargon here, as a bivariate relationship. What we're going to focus on in this brief discussion in this video are those bivariate relationships that we can identify when we are measuring our variables at the interval level or the ratio level. Now, there are other methods that can be used to identify relationships when we don't have interval level or ratio level data, but what we're talking about in this unit is the most common method, are the most common methods for identifying bivariate relationships. We're going to be talking about two methods specifically in this video, using numerical coefficients that indicate the strength and the direction of the relationships. How strongly are they related, and what is the nature, the direction of the relationship? And direction is kind of ambiguous right now. It'll become more clear as we move along. The most common method, again, this is only for interval or ratio level data, but the most common method used for bivariate relationships would be what we call Pearson's R. This was a mathematical method developed by Carl Pearson many decades ago, and it is still the most common method used for identifying relationships between two variables when those variables are measured at the interval and ratio levels. Now, for this unit, or at least for these methods. Now, this unit we have some hand calculations, but you don't have to hand calculate Pearson's R in this unit. Later on in the semester, we might do some hand calculations for Pearson's R. What I really want you to get out of this video is the ability to interpret numerical coefficients, understand what the numbers mean. We calculate these coefficients. What do those tell us about the relationship between the two variables? Also, you'll be able to learn more about how we can use Excel for calculating the relationship between two variables using Pearson's R and the correlation function in Excel. The other method that can be used to identify relationships between two variables is the creation of a graph that we call a scatter diagram or a scatter plot or a scattergram, a lot of different terms used interchangeably for this graph. This graph depicts the relationship between the two variables that we're examining. We'll also use Excel to create the scatter diagram, and be grateful again for Excel. Now, 40 years ago, back in the Stone Age, when I was doing this, we had to do this by hand. We'd get out our graph paper and our rulers and our pencils and erasers and do all this by hand. But Excel allows us to do scatter diagrams very easily, maybe too easily, but it's very easy. And I've got a couple of video tutorials that walk you through the entire process of creating a scatter diagram in Excel. Now, if we were calculating Pearson's R, the correlation coefficient, these are formulas that we could use. Now, believe it or not, these are all mathematically equivalent. And what they're really getting at mathematically is a measure of the shared variance between the two variables. Again, our two variables, x and y, this is a measure of the shared variance between the two variables. Again, these are all mathematically equivalent. And you're probably thinking that this first formula would be the easiest to use. Not the case. There are so many preliminary calculations necessary before you can use this formula, that this formula is really the most complex if you're hand calculating Pearson's correlation coefficient. This formula, you might think maybe it's the easiest to use from a hand calculation standpoint. It's also more complex. The formula that looks the most complex is actually the easiest to use when we are doing hand calculations. And in Unit 12, the end of the semester, we may be doing some hand calculations. I might just so you have the experience, just so you can check it off your bucket list. I might have you do one simple hand calculation for Pearson's correlation coefficient. When I say simple, it won't be a large data set. Maybe 10 different observations. We have 10 X's and 10 Y's. Let's see how they're related using this method. Like I said before, for this unit, you will be calculating the coefficient, but you're going to use the Excel correlation function. And again, there's, like all the other Excel stuff, there's a tutorial that kind of steps you through very simply the process for getting these correlations. And it's one of the easier Excel functions to use, the correlation function. And I've said this 3 times now, may be required for Unit 12, the hand calculation. When we calculate Pearson's R, we end up with one coefficient, one number. That number will range from negative 1.0 to positive 1.0. If we calculate Pearson's R and it's greater than 1.0, there's been a mistake somewhere. If it's less than negative 1.0, we've made a mistake somewhere. It's going to be within this range every time. Now, in this coefficient, we have the sign and then we have the absolute value. The strength of the relationship is indicated by the absolute value. The closer the coefficient is to 1, the stronger the relationship between the two variables. The closer it is to 0, the weaker the relationship between two variables. The negative sign, or the signs, don't have anything to do with it. A negative 1.0 is just as strong as a positive 1.0. A negative 0.5 is the same strength of relationship as a positive 0.5. What the sign does, it tells us the direction of the relationship, whether it's a positive relationship or a negative relationship. And more on that as we move along. It's still kind of ambiguous, perhaps, what we mean by direction of relationship. Again, negative 1.0 is a perfect negative correlation. Positive 1.0 is a perfect positive correlation. Generally speaking, an absolute value less than 0.2 is considered an insignificant relationship. 0.20 to 0.39 is considered a weak relationship. There's a relationship, but it's on the weak side. 0.40 to 0.69 is considered a moderate relationship. 0.70 and above is considered a strong relationship between the two variables. So that's the numerical measure of correlation. Let's talk about using a scatter diagram. Again, and when you look at the relationship between two variables measured at the interval and or ratio levels, you don't just do the correlation. You should also do a scatter diagram, because those numerical coefficients don't tell us the whole story. The scatter diagram can identify some things going on within our data that aren't apparent with the numerical coefficient alone. Yeah, I'll give you an example of this at the very end of this video, but we may have a very strongly related correlation, or there may be a very strong relationship between X and Y, But when we calculate the Pearson's correlation coefficient, it comes out to a positive 0.15, which would be weak. Or maybe it's even lower than that. But when we run the scatter diagram on those data, then we say, oh yeah, there is a relationship. Pearson's correlation coefficient works with what we call linear relationships, or variables that are related in a linear fashion. But if we have a curvilinear relationship, it's not going to give us a good measure of that curvilinear relationship. And again, more on curvilinear versus linear relationships toward the end of this video. With a scatter diagram, what we're doing, we're plotting the data for the two variables on an XY coordinate plane. We're really only using 1/4 of the coordinate plane, that positive quarter, the upper right quarter of a coordinate plane. Once plotted, the pattern describes the relationships between the two variables. And I'm going to show you a lot of examples here before we're done. And if you don't remember what we mean by coordinate plane, here's what we mean. Here's what we're dealing with a coordinate plane. And this is just the upper right-hand quarter of an XY coordinate plane. We have our x-axis, which is the measurement scale for the independent variable. Then we have the y-axis, which is our measurement scale for the dependent variable. And the independent variable is the variable we assume to have a causal effect on the other variable. Again, it's along the x-axis. The dependent variable is a variable we assume to be caused by the independent variable. And notice I have cause in quotation marks. It's very difficult to prove a causal relationship, as we've discussed before. But for the sake of this discussion, we're going to assume some causal relationship between the variables. Again, dependent is the variable that we assume to be caused by the independent variable. And the dependent variable is over here, the measurement scale is over along the y-axis. The values of the independent variable and the value of the dependent variable are used to create a single data point for each observation. Give you an example. If it's not clear, hopefully it'll become more clear. So in this scatter diagram, we're examining the relationship between vehicle mileage and the maintenance cost of vehicles. And that's a pretty simple relationship. We could guess and be pretty accurate with our guess that the higher mileage on the vehicle, the more it's going to cost to maintain that vehicle. Okay, our vehicle mileage is our x variable along the x-axis. Maintenance cost is our y variable along the y-axis. Then we have data for multiple observations, and this is the data pair that we use to create 1 point for one observation, and this is one observation, meaning one vehicle. We have one vehicle that has 60,000 miles on it, that's x, and the repair cost or maintenance cost for that one vehicle is $500. So we plot that point by going along the x-axis to 60, then up the y-axis to 500. There we have the data point for this one vehicle. For the next vehicle, 45,000 miles and $750 in maintenance costs. Next vehicle, 30,000 miles, $250 maintenance costs. Then we have 105,000 miles and $1,000 in maintenance costs. 90,000 miles and $1,000 in maintenance costs. Then we have another vehicle with 75,000 miles on the odometer and $750 in maintenance costs. 61,000, 45,500, 90,750. And then we have this. We have the pattern indicating the relationship between x and y based upon these data. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 observations, 9 different vehicles. And according to the data we have on these 9 different vehicles, we have these data points, and the pattern of these data points tell us something about the relationship between vehicle mileage and maintenance costs. This is what we would call a positive relationship. As the value of X increases, the value of Y also increases. And this is a moderately strong to strong relationship between vehicle mileage and maintenance costs. That's what's indicated by these points. If we draw a line of best fit through our scatter diagram, the closer our points are to that line of best fit, the stronger our relationship. But to know the exact coefficient here, we would use Pearson's R to calculate the numerical coefficient. So we'd have the numerical coefficient and the scatter diagram. That's going to give us a pretty good understanding of the relationship between the two variables. This is not a dot plot. Every semester, I'll have students, they'll refer to this as a dot plot. A dot plot is an entirely different type of graph. It is covered in Unit 4. We're not going to do a lot with dot plots. This is not a dot plot. This is a scatter plot, a scatter diagram, or a scattergram. Those three terms can be used interchangeably, but it's not a dot plot. So if you see that if I show you one of these, let's say on the unit quiz or some of our other activities, and I ask you what type of chart this is, one of your options, if it's a multiple choice, might be dot plot. That's the wrong answer. It's a scatter diagram or a scatter plot or a scattergram. Let's talk a little bit more about interpreting scatter plots and talk a little bit more about this perfect negative, perfect positive correlation, or the negative direction and the positive direction. Over here on the left, we have an arrangement of data points indicating a perfect negative correlation. The line has a negative slope, and we'll talk more about slope toward the end of the semester when we talk about beta coefficients and regression analysis. But a perfect negative correlation, we have all of our lines in a straight line. Our correlation value is a negative 1.0. When all of your values line up in a straight line like this, right on the line of best fit, you have a strong 1.0 correlation. Now, you're hardly ever going to see this in the real world, in real world data, where they all line up perfectly on the line. Usually there's going to be outliers or data points that aren't along that straight line, but that's okay. There can still be a very strong relationship even if all of the dots, all of the points do not line up on that straight line. With a negative correlation or a negative relationship, as the value of X increases, the value of Y decreases. As value of one variable increases, value of the other variable decreases. On the right, we have an example of a perfect positive correlation. Almost exactly what I said about the example on the left, but with a perfect positive correlation, as one variable increases in value, the value of the other variable also increases. And what we saw in the previous example, let's go back to this example. We saw that as vehicle mileage increased, the cost of maintenance increased. Positive relationship. As X increases, Y increased as well. Here are some other examples that might help us better understand the interpretation of scatter plots. In this graph here, we have bus maintenance related to the age of the bus. We have age of the bus as our independent variable and maintenance cost as our dependent variable. Almost a perfect straight line relationship. Not quite, but pretty close. A strong positive relationship. As the age of the bus increases, it's going to cost more to maintain that bus. Older the bus, greater the maintenance cost. In the example here in the middle, we have the relationship between batting average of a baseball player and the number of home runs they hit. There's not any relationship between batting average and the number of home runs. And in the real world, in the baseball world, a player can have a really high batting average but they never hit home runs. Or they can have a really low batting average and hit a lot of home runs. There's not any close relationship between a baseball player's batting average and the number of home runs they hit. There are in the history of baseball, of course, there are some players that hit for a high average, and they also hit for power. They have a lot of home runs. But overall, when you look at all baseball players and their batting average and home run counts, there's no relationship between the two variables. A batter that hits for average is a different kind of player than a power player that hits for power and hits a lot of home runs. So no relationship here, a strong positive here. And over here we have, draw a line of best fit in here, and I'm just kind of guessing. This is a negative relationship, a moderate negative relationship. It's moderate because the points aren't as close to the line of best fit. Over here with this strong relationship, all of our data points were really close to that line of best fit. Over here, not as close to that line of best fit. There's still a relationship going on here. It's just not as strong. And with a negative relationship, and we're looking at the number of days a home is on the market and its ultimate selling price, we see this negative relationship. Home price decreases the longer a home is on the market. The longer a home is on the market, the selling price tends to come down to attract attention from buyers. Some more examples of interpreting scatter plots. Or actually what we got here is a really cool graphic. This is not in your textbook. Some of these that I've been using are in your textbook, but these are not. What we have here are a series of 9 different scatter diagrams. These scatter diagrams range from a weak correlation, a 0.1, all the way up to a 0.9. We have 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9. So you see, you get an idea of what the scatter diagram pattern indicates in terms of the strength of the relationship without considering the sign, without considering whether it's negative or positive. But we also see indications of direction, whether it's negative or positive. Here we have a positive relationship. See how the pattern is that of a positive relationship. Here is a little more negative. It's really a pretty insignificant relationship, but it's a little more negative. You can kind of see that pattern, the way the dots line up. A 0.1, that looks a lot like the batting average home run correlation. That I would not consider that a meaningful relationship once we get to this level at 0.1. And then we have negative 0.4, and notice as the absolute values increase, the patterns tighten up a little bit. And then we get all the way down to a 0.9 positive relationship. It's still not everything lining up along one nice straight line, but a 0.9 relationship is considered a very strong bivariate correlation between the two variables. Now there may be a question on the unit quiz where I give you one of these charts and ask you what correlation is represented in that particular chart. Or I might give you some other scatter diagrams in the unit quiz and ask you to interpret that scatter diagram in terms of the direction and the strength of the relationship. And here are some more. Just to give, I'm showing you all these examples to give you a better reference for understanding and being able to interpret a scatter diagram when you see these data points plotted on a scatter diagram. As I've already alluded to, there will be questions on the unit quiz. You need to understand and be able to interpret the numerical coefficient and also interpret a scatter diagram, the pattern of data points in a scatter diagram. And going from left to right here, we have a positive 1, a 0.8 relationship. Notice how they're further from the line. 0.3, further from the line even than the 0.8. Then we have 0, no real pattern here. Then the same thing over on the negative side. If you have any questions about any of this, let me know. Again, of course, this is also covered in your chapter, but if you have any questions, let me know. One last thing I want to talk about, and we'll talk about this in greater detail in Unit 12 at the very end of the semester. Relationships can exist between X and Y, but the correlation coefficient doesn't indicate that there's a relationship. The Pearson's R is assuming a linear relationship between two variables. But not all variables are related in a linear fashion. There are curvilinear relationships that exist. And this is an example of what a curvilinear relationship might look like in a scatter diagram. Definitely a strong relationship between X and Y. Strong relationship here. But if you calculated the Pearson's correlation coefficient, it might come out, it could be positive or negative, because we have positive direction going on here, we have negative direction going on here. So positive or negative might be the numerical coefficient, and it might be a 0.21, which is a lower correlation. But again, that numerical coefficient is not giving us a good indication of what's going on within the data. There are methods that we can use to understand curvilinear relationship. We will discuss those just very we won't go into it in a lot of detail in Unit 12, but I will talk to you a little bit about how we can make more sense out of curvilinear relationships using nonlinear regression methods. I think I'm going to go ahead and end this video here. Let me know if you have any questions, and I will see you in the next video.